Okay, so many of you won't know me, so I'm Pete Betts, the guy in the front of the name. I've got these co-authors. Laurent's my co-lead in my research group, and Robin's my research assistant and teaching assistant, does most of my teaching these days. And Mark Jessell's the guy who was at Monash University when I was a PhD student, who kind of got me into structural geophysics, which is what I call myself these days, and along with a guy called Rick Valenta, who some of you may know. So that's the title of my talk. I'm going to talk about using structural geophysics, and I'll explain what that is in a minute. And I'm just going to give a case study from the Gawler Craton, and Stefan kindly introduced that to me, so I've got a bit of a habit of having too many slides, so that will assist me going forward. Here's my take-home messages. Before I introduce how I got to where I am. I'm pretty much a regional geophysics whore. I basically, that's all I really interpret there. I don't go and collect much data these days myself. And of course it's a massive advantage. One of the things that we've learned in Australia is that as a cost to collect, it's cheap, really cheap in fact. And it images the crust at multiple scales, so you can actually do terrain, camp, and craton scale analysis using the data sets that we collect. In reality, the thing that I think that's still lacking, and I'll touch upon that in a minute, is actually we don't spend enough resources actually interpreting the data. So we've been collecting the data for as long as you guys have. We're probably a bit more in front in terms of putting it together into a national database and having it freely available, but at the end of the day, there's not many people out there trying to push the data to its limits and trying to do as much as we can. I've spent the last 20 years training people to do that. Most of them get jobs in the mineral sector pretty easily as a result, or other institutions doing similar things. Some of them are much smarter than I am. I want to talk about the predictiveness and the powerfulness of these data sets for analysis. I'm going to talk a little bit about all three scales, so terrain selection, terrain context, and what I mean by that is what's the architecture of that terrain, and can we use that architecture to do something that's predictive, and which goes down to the bottom. So, and when we look at the data, not only draw lines on maps, but also look at it and see if we can say, where's the alteration, what's the kinematics, what does that mean, and can we start targeting using those sorts of ideas and generations? And the last point is about the scale. So let's keep going. Okay, so here's some career-defining feedback that made me want to do this. I'll start. It was interesting, Ken said that it was in Hawthorne in 1993. I was in Hawthorne in 1992 doing my internship, and Tom Whiting was my boss, and a guy called David Moore was my direct reporter, and his job was to print out first vertical derivative images of every survey that they could get, the HP could get their hand on, and my job was to cut them up and stick them on a big board, and slowly in front of me over a 4-month period, a geophysical image of the Australian continent appeared in front of me, and I was like, wow, that is so cool, and that's when I got inspired. I didn't really know what I wanted to be. I never wanted to be an academic. I just kind of fell into that, so I call myself the accidental academic. But I did have some career-defining feedback, and then the last one, which is that made me think about what I do and why I do it. Here's the first one. Shame you're doing structural geology. You could have been a good geophysicist. That was my professor of geophysics, Jim Cull. That was in 1992 when I was doing my honours year. And then my PhD supervisor was a guy called Gordon Lister, who was a structural geologist. He says, pity you like geophysics because you would have made a good structural geologist. And I'm sitting there going, wow, okay, I'm crap at both. All right. So the other influential quote is from a guy I did my PhD with at Monash University many moons ago now. A guy called Marco Davis. Some of you will know him from Oxygen Capital these days, but he was at Frontier Group when he talked to me, and we sat down and had lunch after I'd just been up in the Yukon doing some mapping for a small junior company, and he basically said this: I'm sick and tired of forking out $100,000 a year for an undergraduate who goes out in the field, he's too scared to put a line on a map. And he said, I didn't care what the line was, right or wrong, I just wanted something, and he swore at me, and he wanted to work with it. So what he was basically telling me was, there was a lack of confidence in the graduates that we were teaching to actually just go and put a line on a map. And so I went, what's that problem? And it actually became really obvious when I started teaching fieldwork, and it was just about confidence and people's inability to cope with the ambiguity of the data that we have to work with from a day-to-day basis. And that's a learned skill, and if you encourage people to just do it, you get results much more rapidly. So that's one of my motivations for what I do. Today's event is about David. I didn't know him personally. He retired just as I was coming onto the scene. But I did, Ken sent me this paper, said, have a look at this. And I started reading it and I was like, wow, we really do reinvent the wheel from time to time. And those first 2 points, he's nailed the whole thing, but the first 2 points are the things I want to highlight. He basically nails it in the first sentence. He says, the most important step is to understand the geological problem you want to solve. So anytime you do I do a geophysical interpretation, I don't even call it a geophysical interpretation, it's geological interpretation using geophysical constraints. You have to ask yourself or the client what they want. And that completely dictates how you deliver it and how you deal with it. The second one is, he uses the word contour maps, but it's really about translating a physical property of the Earth. In case of magnetics, it's the distribution of magnetite pretty much into the Earth's crust, and how you take that physical property and you turn it into a geological process. And that is actually not a trivial thing to teach someone, nor is it a trivial thing to do, and I think it's the biggest hindrance on why we don't have many people floating around being able to interpret these data sets with much confidence. Okay, so what's structural geophysics? Because you're going, what the hell's that? And it's basically the application of geological structures and basically applying structural analysis techniques to regional and detailed geophysical data sets. And I'll tell you why there's such a parity between those two. Basically, if I look at a geophysical data set, I'm looking at three things. I'm looking for three-dimensional geometry, and that mag image there tells you a lot about the three-dimensional architecture of that piece of, or that volume of crust. The overprinting relationships, and that's the sequence of events that led to that three-dimensional geometry. And then you can do the kinematics as well. So you can look at what's moved and when, and that tells you how the rock has got there. And you can do that at all scales. So for me, the transition from structural geologist to structural geophysicist, I don't think that's hard, but there is some problems. So, and this is it, and the main problem is around education, how we teach people. I listened to the previous talks, and Matthias put his hand up and said, I'm a structural geologist, and Victoria stood up and went, I'm a geophysicist. And to be honest, I don't even know what I am anymore. Some people in my corridor in my school think that I'm a geophysicist because I teach the geophysics course, and some people think I'm a geologist because I teach the field course. But in reality, I don't see myself as either. I just see myself as someone who uses geophysics and structural geology as a tool to solve problems. So I think we have to stop using the language of I'm a geophysicist, I'm a structural geologist, and start to try and create graduates who are competent, not necessarily expert, in both of those discipline areas. So if you're a structural geologist and you're wanting to look at these data sets, you really struggle. You go, where do I start? Where do I start putting a line on a map? That's always the first question I get when I teach it, how to do an interpretation. There's almost zero understanding in the geological community of how these data sets are processed, the limitations of it, and what you can get out of it and what you can't. Until we start having people, geologists, understand that, they will never be able to really effectively interpret it. And then, as I said before, in turning that one petrophysical property into a geological observation. Now, if you're a geophysicist, you don't get off lightly either. Usually, my experience is when I go and do a consulting job for a company, they know not much about geology, and so if you don't know what a fold and thrust belt looks like, how can you interpret one? So that's a challenge, and I think we should be encouraging more geophysicists to go to geological short courses and start to get their head around it. And interacting with geologists helps as well. And that's the last point I made, which is how do you interpret something if you don't know what it looks like. Okay, so I'm going to start from a large scale, and I'm going to go down slowly into basically a camp scale problem. So from a mineral systems approach, which is what I'm talking about, I've got two figures there. One's basically an image I stole off the USGS website, which shows all the copper deposits around the world. What's obvious if you look down the Americas is that all copper deposits form in the overriding plate. Okay, that's nothing new to anyone on the planet, even my first years know that information. Okay, the problem is when you go up into Central Asia, into the Altides, where there's all these copper deposits, but they're all stitched together by many terrain accretionary events. So how do you pick which is the overriding plate and which is not? So that's a big question I always ask myself is when I'm looking at some sort of prospectivity analysis, am I standing on the downgoing plate or am I standing on the overriding plate? Because that's actually super critical, because if you go on the downgoing plate for a certain period of time, or that time period you're interested in, you're probably not going to find something. And even the guys that work in the ancient, well, that's not what I want to do, I want to go that way. So even the guys that work in the ancient terrains, they basically recognise that all mineral systems forming in the overriding plate. We know all the chemical reasons why. They've listed them, pretty much listed them there. High heat flows high, active and intense deformation to drive fluid flow through the crust, transient switches in tectonism, so switches from extension to shortening is super critical, intense magnetism, so that's more fluxing of a different kind, and you always get better preservation of the overriding plate compared to the downgoing plate. So that's the first question I ask. We have two challenges in Australia. We're really good in Australia finding ore bodies that the old guys found in the 1880s and just upgrading them. We're also good at finding ore bodies that exist at 50 metres depth or above. You're hoping I was going to say below, but I don't. And then as we get deeper, we get worse. We do have our flagship deep ore deposit, which Stefan talked about, which is Ailleres Dam. It's a massive ore deposit, many of you will know that, and it's at about 350 metres depth. So that's our one deep super discovery. Most structures, most of our ore deposits are structurally controlled. And I would argue, there's a lot of talk about making a map undercover. I would argue it's actually about making a structural map undercover, because they're the things that we can use to target. Okay, and what I mean by that, it has to be in 3D, kinematics, and it's got to have some predictiveness. Some of the biggest challenges we have is finding our ancient boundaries, because our continent has been modified multiple times, so it's a reworked continent, so the original boundaries of the accretion events are not always the same as well. What are the signals that will... I've got to get better at this. What are the signals in the geophysics? And once we've identified them, what are we really doing with this? Okay, so here's some geophysical data, which is what I'm going to talk about. About 15 years ago, we set out to collect a whole series, we being the Australian geological community, set out to collect a whole series of regional seismic traverses, much the same as the lithoprobe program here in Canada, and it was a game changer. Because for the first time, we were able to image big structures, offsetting mohos. This one's an ancient suture zone, it's called the Gidya suture. It's actually located along here on the eastern side of the Mount Isa belt. And all those seismic lines started to give us some serious two-dimensionality in the vertical plane. And then we were able to use our excellent geophysical data sets and start mapping them out in a more regional context. So at some sort of large scale, we're able to pick out the major suture zones. So some of them are not very long, so we lose them, and that tells us something as well about the reworking. But importantly, we suddenly knew where the overriding plate was and where the downgoing plate was, and that makes a massive difference from where you might want to go and start exploring. So this is just a reconstruction of those suture zones. So this is a recent paper that I published last year, and basically we did G-plates reconstruction. We stuck the geophysics into it because you can't bend it, you have to cut it up into slices, but basically we took that really complicated mosaic and made what was a pretty simple structural pattern for the Australian continent. It's a series of ribbons that all accreted on together, and we can strain that between about 1860 and about 1800. So it's a pretty rapid accretionary event, and that's the template from which the rest of the continent formed. But that was based on, and only could be done because of the regional geophysics that was collected in the last 15 years. So even at that scale of the continent, it's really kind of important because you can start to understand those first order problems around mineral systems. What play do you want? Okay, so you need a method for selecting what's the position of a terrain or plate boundary. Okay, and usually it's done with a combination of seismic and gravity, and then the magnetics gives you the surface expression. You need to understand depth extent, so the long wavelengths, and you need a method to map it. And so even though you've got a 2D image of a structure, you actually have to take it into the third dimension. Well, another plane, still 2D, and trace it along its length. I don't want to go through all this too much, but basically it's not easy. Sometimes the signal's cryptic. For example, we don't see too many blue schists in Australia, so that's hard, and not many ophiolites. But usually you can tell when there's a big step in the moho. You usually have large strike lengths, which you would expect because it's a plate boundary. In the absence of seismic data, we use gravity, and we look for changes in geophysical response, so the texture of the geophysics across these structures as well. The interpretation is ambiguous. I'm going to give you an example of that in a minute. And the geology on either side of the boundary should have different history. So if you go back to the geology, it will tell you something about that history. Here's some plate scale, lithospheric scale structures from the Musgraves. This is a PhD student of mine from many moons ago too. He worked in the Musgrave block, which is up in Central Australia here. He did geophysical structural interpretation. He actually interpreted the lithologies as well, but not in this paper. This is the gravity anomaly, and this is his forward models across that. The interesting thing is that gravity anomaly is being caused by basically a preserved uplift moho that's about 550 million years old. So it's been in isostatic disequilibrium locally for 500 million years. And what he did was he basically built a whole series of forward models, and then he created a 3D model, and then he ran a series of VPMG inversions at crustal scale, and these are the results of those inversions, and these inversions are picking out all the structures beautifully. It's a great piece of work, but it basically shows the power of integrating regional geophysical data sets with the geology, with these new technologies, the inversions that we are doing. That was done about 8 years ago now. So I'm going to talk about a case study, which is the iron oxide copper which Stefan talked about. So the IOCG story is really a story about two provinces, the Gawler Craton here, and then Mount Isa inland, which is to the north. They both host IOC mineral systems, large ore bodies, at different crustal levels and at different times. And then when you speak to people about what causes those IOCGs, you know, it's like, let's put some money into a pot and pick out a lucky winner, a lucky dip. But plumes is one that people invoke, and there's evidence for a plume. Proximity to a plate boundary, crustal lithospheric scale faults, as Stefan pointed out, craton scale normal fault controls, so there's a lot of work out there now that's showing that these mineral systems, like the original targeting strategy for Olympic Dam was, looks like they're upper crustal features formed in extensional basins. So the sedimentary copper model that was originally developed for it, whilst not being quite accurate, we've done a full circle and have come back to similar models. Low metamorphic grades, sedimentary basins hosting that. Some people believe it's an unconformity control because it's a chemical boundary, not dissimilar to uranium deposits, and then you have high heat fluid fluxes caused by tectonic switching. So there's a distribution of, this is basically eastern to central Australia. That's the Gawler Craton down there. This is the Curnamona province, and this is the eastern fold belt of the Mount Isa inlet. And the yellow circles there are all the IOCG provinces. It's basically 1,000 kilometres in length in present day coordinates, and the mineralisation from the youngest one here in Mount into the Gawler Craton to the oldest one up here is about 90 million years. Okay, people have often speculated whether it was the same province, and we went out to test that because of the similarities in the mineral systems. And so what we did was we used this geophysical data. We applied the data to a regional reconstruction that a colleague of myself and I did about 15 years ago. We rotated the South Australian craton here about 55 degrees, and this ended up being the architecture. Now that's great, they put them closer together and almost in a straight line, and we went to see if they were actually genetically linked, and what we did was we took the paleomagnetic data of two poles of Australia leading up to this mineralising and magmatic event, and we tracked its trajectory on the Earth at that period of time. So that's the Euler pole for that. And then what we did was, at the point of the last paleomagnetic pole was exactly overlapping with this event. So we knew where we were in a point of time, and we plotted this magmatic and event on top of Australia, and it fitted the same small circle as that polar rotation. So what that really means is that this is a hot spot that starts off at 1580-ish here, ends up at 1500 there, and it was tracking along the same trajectory as the paleomagnetic data. So we had a test, a positive test, to suggest that these are at least genetically linked in time and space, which is kind of neat. The Gawler Craton is a very cool part of the world. Stefan touched upon it. The magmatism there, the Hilton event we call it, is basically a series of high temperature granites, and that's the scale of it there. And then there's this huge, large silicic igneous province. It's bimodal, but the mafic component of it is incredibly small, and the felsic part of it is enormous, and it is expressed beautifully in the geophysics. So you can see it through here, and actually you can see these lobe features here, through there, and you can see them, they're a bit buried there, but they're there. They're lobe fronts of that volcanism, okay? And if you draw a line that's roughly orthogonal from them, it's basically all sourcing from the same area. Now the cool thing about these rocks is that they have flow paths, lengths of about 100 km. So in order to do that in the way I knew volcanology, you needed an ignimbrite, but all the physical volcanologists were telling us that they were lava flows. And you go, well, that's not possible, because they should be gooey, just rolling down the volcano. And as it turns out, the halogen content in these rocks is so high that it turns the rheologies into of these silicic rocks to that of basalt, which is really weird, but pretty amazing. I don't know why I said that, I just find it really cool. Anyway, I'm talking about regional kinematics for a while, right? So as a structural geologist, I can go walk up to any shear zone, and if I sniff around long enough, I'll be able to figure out how it moves if it's preserving some sort of kinematic indicator. And I usually look for these things. Porphyrclast or porphyrblast with some sort of morphology that suggests it's been rotated, okay, or recrystallised because of the flow around the rock. We look for SC fabrics, microfiche structures. Here they are, that's a microfiche, there's an SC fabric there. Look for asymmetrical fold trains, which or flow perturbation folds we sometimes call them, and deflections in foliations. So for example, here you've got a shear zone there, and this foliation has been deflected around like that, and I can tell how this block is going that way, and this block here is going that way. So we can do that. But actually, if you look at geophysical data sets, I'm not going to bore you with this, except for to say, you see the same patterns, like you've got it in your notes. If you read down this, you see the same patterns. The physical characteristics of those patterns are different, but you can still read them the same. That's what the take-home message from that slide is. And the thing is, we can look at these things, I think geophysical anomalies are planar fabrics and volume elements, and then we can make some call about the kinematics. And I'll give you some examples in the next slide. Okay, so here's a thin section taken out of a classic textbook. And you can see the C prime plane, and then you can see this S-band here, and that's telling you that this is basically the way we're looking at it, a sinistral shear zone. This is in the Gawler Craton. Here's the C, it's equivalent to the C prime bands, and you can see the curvature of these magnetic anomalies telling you the same information. They're almost identical. So we would hunt around, and we see these everywhere, and we start looking for them. They tell us a lot about the movement of these structures. Here's another one. This is just to the north of that previous location. Here's a delta porphyrblast in this case, and it's been rotated and recrystallised at the edge. Here's the same shape in the rocks. Now, you might go, oh, you're just making that up, but actually in reality there's a big shear zone here called the Yerda shear zone. It runs up here and it actually outcrops there, and it's the biggest dextral shear zone that you'll ever see. So it's actually telling you the same kinematics. You can see similar patterns up here with these tails on these granites here. So we look for these things all the time because they tell you lots about the movements of faults, and when you know how they're moving, then you can predict things like dilation. So that's why we think it's important. Right, let's keep going then. Okay, so the kinematics is a valuable tool because it tells you about large-scale rocks, geometrical criteria that tells us about the regional scale movement history. We relied on planar features, and the criteria is most effective for structured faults. Obviously, if there's a vertical fault, we don't see that as kinematics. And from a mineral systems perspective, It's used to predict the size of dilation and therefore fluid flight, which is important if you're going to look for ore bodies. Okay, so I was sitting in the outback once with a colleague of mine. He told me I was a waste of oxygen because I didn't do anything that was useful for mineralisation for the state of South Australia, and he was a government worker. And so I took on the challenge, and what I did was, at a terrain scale, I picked every fault that I could demonstrate was active during the Hilton event, so I used a whole series of criteria, and then I applied that kinematic toolkit that I just showed you to the faults and mapped them out, and lo and behold, when I looked at this pattern, I basically had a master fault, which is the Ailleres shear zone, a whole series of second order splays coming off it. Interestingly, off those splays is all the big mineral systems, so that was kind of telling me something interesting. I didn't know what the significance of that was, but more importantly, well, not more importantly, but what it did was, I was really restricted in how I could interpret the kinematics, and that's basically what I had. So we basically had an extension direction in this direction. These faults were structured faults. These faults through here were normal faults. That's the story. You can't argue that. That's the kinematic regime that was operating when these mineral systems formed. Okay, so when I would go and look at a more detailed mag interpret, it's not mine, it's Nick Doreen's. He had a series of faults. He didn't really want to call them what they were, but in that kinematic regime, which is the extension direction this way, we now know which ones are the normal faults in that system, which ones are the transverse faults, and interestingly enough, it's the opposite to what the people at Olympic Dam think. Because they've got these isolated little basins with no structural control, they're just sitting in a hole. They don't really know, they've got no flow direction, they just assumed that this lot here were the normal faults and these were the extensional faults. But the kinematic analysis on the regional geophysical data says that's not possible. So in more detail, I've honed into a place that's dear to my heart because I did my honours there in 1992 and I keep revisiting it. I've done 4 different mag interprets of this region with different data sets, each one higher resolution. This time around I was asked to do a terrain scale analysis so that the geological team at Oz Minerals could understand the context of their terrain, and they were about to spend $70 million in 1 year exploring this region. Okay, so they wanted to understand the architecture of the setting, they wanted to know where the rock types were. I got whatever rock, drill holes that they had, plus whatever mapping was done, including the one my previous mapping, and I had to identify alteration and also the tectonic evolution of context, and that was going to help them predict stuff. I should say, I'll go back, Prominent Hill, well, this way. Prominent Hill was actually targeted on anomaly. This is a skarn, it's got nothing to do with mineralisation, that's what they targeted. It's got basically a gravity anomaly that's next to it, and that is the water closet. So that's what the data looks like. It's spectacular. It's 12 metre grid, so it's really, really nice to work with. Took a long time to interpret the detail. That's part of the interpretation there. You don't need to know about the details. The point I want to make here is, when as a geologist, sometimes, you quickly grow to understand that the language of geology is actually maps. So if you want to communicate with geologists, you actually have to make a map for them. So if you're not making a map that they can stick on the wall and look at for a while and ponder, and actually the effectiveness of the work that you're doing is actually quite limited. And that's just my philosophy, okay? And that map has to make sense, so it can't be a nonsense map. And basically, this becomes the context upon which people start making decisions around. Okay, so I never get asked to pick a target. I basically get asked to give someone some context. Okay, and of course, when I'm making that map, I'm always thinking about the geometry, the kinematics, the alteration, and the overprinting, and as I said, in the map format. That's the outcrop. Not much. I did my honours. I mapped that little one there. It took me about 4 weeks. I was really slow and pretty hopeless. We're sitting up there in this part of the Gawler Craton there. I think processing is really important. I actually do my own processing, so if someone says, what level of processing do? I do it all, but I don't level it or anything before that. Real geophysicists have to do that because that's really hard. But I'm happy to do any sort of filtering and processing, and I tend to be a bit more cowboyish at times, so I like to mix and match and see what works, and it makes some people really uncomfortable. That's basically the RTP image there, and you can see there's it's a pretty low terrain, but that's the Greyscale of the second vertical derivative, and stuff is starting to jump out there. Normally I wouldn't do it with that second derivative. The data was really clean, so yeah, it was great to interpret this stuff. That's a close-up of it. This is basically the Greyscale of the second vertical derivative on the Bouguer gravity data. So you can start to say, by mixing and matching the two images, you start to see all sorts of patterns. Okay, let's keep going. Yeah, I think I'm okay. If I get through, it'll be a miracle. So no, so that's basically a map. So and that's the regional scale map. And two of us did it. So we both worked closely together. It took about 8 weeks of total work to do that interpretation. All I want to say about this is, at the end of the interpretation, what I discovered was that if you double the resolution of the data, it takes twice as long to interpret. The other thing I'd say is I have a slightly different approach to the other people who've spoken today. Is I tend to use the geology as a starting point, and then I build out from that. So I basically start with whatever information is known, and then I start following those units like I would if I was actually physically mapping rocks on the ground. So that's my approach, and I tend not to map to a scale. I just map to what I can see. So if I can see something in small resolution, I'll just zoom in and interpret it, and then if I see something that's bigger, I do it. So I just cross scales pretty much the entire time. So that's kind of the approach and philosophical approach that I like to use. The interesting thing about Olympic Dam and the Gawler pattern, I do need to point this out, is that they're both sedimentary hosted systems now. That's been recognised, okay? And in Olympic Dam, Prominent Hill, they recognised it about 7 years ago, and they kept it quiet for a long period of time, and they had this breccia system from a package of rocks called the Prominent Hill Group. It's an older package of rocks that was pretty much unmetamorphosed, and then it was a breccia. So this is the ore system here, and these are the breccias with all the alteration, hematite alteration, and this is what it looks like when you step away from the ore system. And what we were able to do in this project is we started to map out or differentiate the different packages of rocks. And the reason why they were interested in this is because it became very clear that the only package of rock that was hosting mineralisation was this thing called the Prominent Hill Group, and it was actually restricted to a really narrow belt along the southern margin. So they'd spent about $20 million drilling bullseyes outside of that unit and wasting that money. There was no mineralisation attached to it. And then once we said, look guys, it's hosted in this, and this is where the geophysics is telling us where this unit is going, they started to really focus on that, and they did find sniffs along that package. Let's keep going. In terms of structural evolution, we did have a breakthrough at one point. We were recognising these sort of half-graben morphologies in the Gawler Range volcanics that were undercover, and that's the geophysical expression there. They have that sort of wedge-shaped stratal geometry, and we're recognising those as big normal faults, and we weren't seeing them going too far into this basement terrain. And my good friend and colleague John Stewart and I were out there one day mapping, and I said, let's go and find the northernmost outcrop and see what it's telling us. We basically walked out onto this fault here, and it was a proto-myelinite exposed, dipping about 30 degrees to the south with normal fault kinematics, and that was the game changer, that one geological observation, because it meant that this fault that was wrapping around like this actually was a normal fault. And what we did know was that these rocks were all polydeformed gneisses, and these rocks were generally a lower grade. And then so that led to us interpreting this as basically a truncated half of the preservation of a metamorphic core complex, and with normal faults on the outside of it, and the lower plate preserved on the inside. And then subsequent geochronology proved that fact. These rocks are about 200 million years older than these rocks sitting out on the outside of that, which was a big breakthrough for us. There was also a structural overprint of a shortening event. So these are elements of the geophysical interpretation showing the folds in this case. That's quite an open fold, causing this granite here to be, this unit here to be doubly plunging. The actual ore deposit here sits in here, and there's a duplex system that's basically thrusting rocks back over the top of it. We think the ore deposit formed in pretty much flat stratigraphy, and it's now been tipped vertically as a result of that duplexing. And you can see refolding of an earlier fold generation through this structure through here. So we had an understanding there was an early extension event, and that was overprinted by, that's the early extension event, with the bits that we were thinking were dilating in that structural architecture. And then, last slide. And that's the shortening event. That's the structures that were active during the shortening event. These days, we teach the kids to map on paper, but actually most of the time now, we do it straight into GIS. We basically attribute everything as we go. So if we think it's a normal fault, we'll call it a normal fault. We give it a scale, for example. So we'd say first order fault, which means the big one, second, third, fourth, fifth sometimes. And any kinematic information we give it, so then we can pull that information out of the GIS pretty rapidly. So that's pretty routine and part of our workflow now. So we don't do anything on paper anymore at all. Okay, so that's basically the last bit. I can't tell you where we targeted some stuff for them. They asked us to do it in the end. Can't talk about that, but pretty much the method was, we know these are the faults that were active. Where will they be dilating? That's the prediction. We now know that all this stuff here is useless because it's not the right stratigraphic package. This is the stratigraphic package they're interested in through there. So some of these targets became high priority because of that. So I didn't talk much about alteration, but actually what I would say is, and as a parting statement, is that magnetics in particular is really sensitive to alteration, and when I'm mapping I look out for that all the time. It's usually in the form of either magnetite enhancement or magnetite reduction, depending on whether you've got an oxidizing or reducing fluid going through the crust. In this case, magnetic anomalies weren't that important, even though the original ore body was targeted on a false anomaly that actually had nothing to do with mineralisation. But the magnetic interpretation was required to give the context. Faulted intersections and location of dilation sites at several scales became important, and that dilation can only be done if you do the kinematics. The unconformities were important. That's becoming increasingly apparent in mapping those out, so I didn't talk about that, but that's one of the things we did. And I think the proximity to these Hildebrand granites is important because of the heat fluxes. It's the heat engine, it's the energy in the system through there. And this part of the world of Mount Maginla has a large suite of these granites, and actually mafic parts of the system as well. And I think Stefan pointed out, if you're close to a big lithospheric scale structure, that's actually the primary reason to be close to that, and it's the other things that I've talked about, which is superimposed on that actually starts to focus the mineral system. Okay, and then you need to think about where you are in terms of your crustal level. And I'm just going to stop. Okay. Yeah, thank you. Cheers.
Got time maybe for one question for Pete? So.
Just following up on the last point, from primary to secondary, tertiary structures that you have. You had one map where you showed your location of the deposits versus the faults, that came off the yellow fault.
Yeah.
Do you have a feeling, if you look at the secondary and tertiary structures, where they would sit? Is it fault density? Is it relation of strike slip versus normal faults where you would find them? Have you thought about that?
So there's three things at play, I think, Stefan. So your lithospheric scale fault is an old sutures that runs up there somewhere at within 30k width or something like that. So that's the primary plumbing system. Those faults, the Yerta shear zone, they're large structures. They've got probably hundreds of kilometres of offset, some of them, and they certainly have a primary influence on it. So some people might say they're primary, but compared to the terrain boundary, they're second order structures. And so, and then the ore systems along them are not exactly at those junctions. They're actually at the junctions as third order structures that are interactions between those transverse faults and those normal faults. So it's actually, what all those structures are doing is honing in where you might want to start putting an exploration license around. Then you have to start looking for the smaller structures. And orogenic gold faulting systems are the same. You look for perturbations in them and fracture zones. So yeah.
Okay, we got a bit of time and end, but we'll let Pete go now.